Hey, this is Tejasva Soni of Branch Integrated MSc Physics, third year, and I'm here to present on topic pulse width modulation and how to create it on Intel 8085 microprocessor. So let's see. So I'm gonna start by giving you an intuition how pulse width modulation works, and this is just a real life scenario. So this is the case of we have a switch which controls a ceiling fan. Observe that if we keep the switch on, the fan gains the speed and it attains a velocity, and then if we put off the switch, it loses it slowly. So when we keep alternating this in a periodic manner, the fan averages this out, and you will still get a saturation speed of the fan which will be lower than its earlier saturation speed when we just kept the switch on. You can try this, like switching on and off, and the fan will gain the speed and then lose, gain the speed and lose, and due to inertia it will just attain a saturation where this effects will neutralize. PWM. It is a way of delivering energy through a succession of pulses at an adequately high frequency rather than a continuously varying analog signal. So, analogous to the fan and switch case, like we are giving pulses of on and off at an adequate frequency, which should be high. As if it was low, then fan will saturate to the off situation, and or it will be gaining its top speed, but we have to do at it adequately high frequency so that the neutralization effects take place. And as the name suggests itself, the width of high and low pulse have different duration in a cycle, and this decides the average output voltage observed. So if I and still analogous to the freeing case, the if we keep the switch on for a long time and keeping off for a less time, obviously the fan will gain more speed, more saturation speed. Thus it kind of fakes an analog like result by applying power in pulses or short bursts of regulated voltage, and the output ends up behaving like the average of the pulses. Yes, you can get this by our analogous of fan and switch case. So the we could have done this by putting an analog power to the fan, like increasing the voltage slowly, but we can do this by faking an analog signal by giving pulses of high frequency and just putting it on and off in certain times. So let's get into the details of PWM and how it works. The duty cycle is defined as percentage of T on with respect to the total period of the signal. So this is the total period of a cycle of a signal, and T on is the time period we keep the high pulse, and T off is the time it keeps the pulse low. So duty cycle is defined by T while it is on and the total time of the cycle into 100. So it is kept at 90% of the time on of the total time of cycle, then it will be 90%. So the average voltage, which we call the output voltage which we want as an analog output, will be equal to duty cycle into high voltage level. High voltage level will be this one, which could be like in our case 5 volt or 24 volt according to the microprocessor, and into the duty cycle. So in this case it will be 50% of the highest voltage. If it was 24 volt, then the average voltage will be 12 volt. So this is the our general case where we will see how it works. So this is our PWM pulse, uh, and as you can see clearly see it is a digital in nature, like it can only be high or it can be low. So here it is high and here it is low. So you can see that this here is the range where the time period of keeping it on is high and it is kept at low for less time, while where it is rarely dense, you can see that it is kept high for less time and it is kept on low for more time. So when it is kept high for more time, or you can say where the duty cycle is more, you can get more output, and where the duty cycle is less, you get less output, which is T average. Here is a loop you can see, and we start the flowchart here. So we want to create a pulse like this. So first we set the loop output of the pin loop. This is the low part, and then we give a delay of T low time. So this is the T low time from here to here, and then we set the pin high. This is the high, and then delay the and to set this pin high for time T high, we give delay. So this is the delay we give to keep the pin at high for time T high, and then we keep repeating this pattern till this whole cycle repeats itself again and again. Now we come to our code. So this part initializes ports as output. We write this assembly code in these are the mnemonics, and we write this assembly code in our 8085 memory segments. So this initializes ports as output, and this jump mnemonic puts to the location of a loop. So this puts it on this location. So now we come to our main loop, MVIA00H. So this puts 00 into accumulator, and this byte is outputted to the 8255 chip, so that makes the output low on port A. Now we come to our how we put delay into our output. So we call the delay function, and give this delay as parameter to the function, which create a delay of time low. Now similarly, this is how we put high, and this is how we put low, and this is our delay of low, and this is the delay of high. And now this loop, this is an unconditional jump loop, and this again jumps back to the location of loop. So this keeps happening, and we get pulses. So these are the pulses which goes low, high, low, high, low, and high. And these are the delays we set by using that delay function. Now delay can be manipulated using T high, manipulating T high in our earlier code by manipulating this value and this value. So to change the duty, and if we want to increase the duty, we increase this time, and to decrease the duty, we decrease this and increase this. So by adjusting delay value of T high and T low in the code, we can obtain any intermediate average voltage as the output. Now to get an practical intuition, we put this code and try to make an LED brighten, fade and brighten. We can't connect LED directly to our microprocessor because it draws high current, and our microprocessor isn't suitable for high current flows. Thus we need a interfacing chip like 8255. And when these all cases happen, and when out 00H is executed, accumulator data goes to the data bus on the next cycle, and then is returned to port A. This is the use of 8255 interfacing. So when out 00H is executed, it goes it initiates port A as our output port, then accumulator data goes to data bus, and data bus writes our data to port A, and thus we get our output at port A. So now we come to the hardware segment of our pulse generation. So this is our 8255 interfacing chip, which we use to uh, interface our LED, which is our output device, to our 8085 microprocessor. So when we, and this is the port A, This is our LED, which is connected in series with a current limiting resistor. Then it is grounded and it is connected to the first bit of our port A. So when out 00H is executed, the data on the accumulator goes to data bus of our 8085. Then when out 00H is executed, thus this data on the data bus goes to port port A of our 8255 interfacing chip. And then on the next cycle, which is the first bit of our port A is connected to the LED. So uh, after each cycle, what is the output on data bus goes to our LED. So by adjusting delay value of T high and T low in the code, we can turn different brightness of LED. So by adjusting the Ti and T-low, we get analog output at our LED, and we can make it fade brighten by increasing this time and decreasing this time. So now let's check how this practically works. So when the duty cycle is 75%, which means this time of signal being high is 75% of the total time, we get a 75% duty cycle, which will be the which will make the V out 75% of the our reference voltage high. So the LED will brighten very high, and when it is decreased to 55%, which means T high is equals to T low, we get an intermediate brightness on the LED. And when the duty cycle is 25%, then we get a very dim LED brightness. So this is our analog output. We can get any intermediate brightness of LED by varying this T high and T low of our signal, which we get through 8255 chip. So we are getting an analog output through digital pulses of PWM. So that's how PWM works and how we can create PWM on 8085 microprocessor. So thank you. That's it.